Can you hear me? Yeah, you can hear me. Transverse waves have the shape of a sine curve, and you can see sine curve right here. This is what a sine curve looks like. And you literally have an x-axis and a y-axis, and you can put these transverse waves on the x and y axis. And it's called a sine curve. Sometimes it's called a sine wave, and we can actually do a lot with that. You may remember the rope mentioned in the last video. If you were to grab a rope and pull it up and down, it would actually look a lot like this. So you can see how this would be a transverse wave, the energy going up and down, but the wave is actually going out. A crest, I guess I better get one of these. A crest is this point at the top of the transverse wave. The crest is the highest point on a transverse wave, and you'll find later you can have them with these longitudinal waves also. The trough is going to be the lowest point. Up here crest, up here trough. The amplitude is the greatest distance from a resting position. Now the resting position is going to be at the x-axis. So the greatest distance is either going to be the measurement from the x-axis to the crest or from the x-axis to the trough. It should be the same distance. So those are some terms that we can get from these graphs. Now we've mentioned these transverse waves, and that this is an example of a transverse wave on an x and y axis. However, we have not mentioned longitudinal waves. Longitudinal waves kind of look like a slinky, and here's a slinky-like looking impression of the waves. Now there are some places on here that are different from others. You may notice that we have an area called compression. Compression are these crowded areas on longitudinal waves. And you notice that we have this place called rarefaction. Kind of an interesting name. Rarefaction is whenever you have these stretched out areas. Now you can actually, scientists can take these compressions and rarefactions and actually have the compressions down where the troughs are, and the rarefactions up here where the crests are. So you can literally have a graph just like you did of these sine curves of this compression and rarefaction, and it would look just pretty much exactly like these would. It would have the trough, and it would go up to the crest, and it would go down to the trough again, and it would go up to the crest, and all these troughs would be the compressions, and all these crests would be the rarefaction. So you can have these terms, crest, trough, amplitude, for more than just transverse waves. You can have them for longitudinal waves also. Oh, let's see, I think I'm going to need to go to another picture. Okay, let's talk now about wavelength, period, and frequency. Wavelength is the distance in meters from crest to crest. That is the wavelength. Now this would also be the same length if you were to go from trough to trough. Talking about length here, and this is going to be called wavelength. Wavelength actually is kind of like an upside down Y is going to be the symbol for wavelength. Now both transverse and longitudinal waves have a wavelength, because remember you can put this in both kinds right there. Now let me talk about what the term period means. Period is going to be called T. The symbol for period is T, which will be easy because it's in time. Period is the time required to go from crest to crest. So the time required for one wavelength. The time is period. The distance is wavelength. So you can probably figure what frequency is. Frequency is going to be wavelength per second. Wavelength per second. And you would be amazed at how many wavelengths you can have per second. So let me put the whole formula here. Frequency equals wavelength per second or per period. Now, whenever this is actually going to be in a term, in a unit called hertz, which is H-E-R-T-Z, but it's abbreviated H-Z. I wish I had brought my tablet in which to write on, because this is a little bit difficult. But anyway, frequency is going to be in hertz. Now, we can hear frequencies from 20 to 20,000 hertz. Wow, 20,000 wavelengths per second. That's a lot of up and down on a sine chart, on a sine wave. But yes, we can hear things that are 20 to 20,000 hertz. The higher the frequency, the lower the time period, and vice versa. Now, that's going to be a whole different ball game with light waves, because you know these electromagnetic light waves are just a little bit different. Let's talk about light waves. Light waves are expressed here. You know, we see all the way through the spectrum, the purple all the way through into the red, into the dark red. Now, we can detect light waves from 4.3 times 10 to the 14th hertz. Now, this is going to be in your book, and it says in meters here, so that's why it's 10 to the negative 7th here. But it's going to be 4.3 times 10 to the 14th hertz. Wow, that is 4.3, and move the decimal 14 places. That is like trillions or quadrillions hertz. What an incredible number of up and downs you would have for that. It's just hard to even fathom. And the light spectrum goes from 4.3 times 10 to the 14th hertz to 7.5 times 10 to the 14th hertz. That is visible light. And if you notice, there's only a little bit of visible light. There's all these other frequencies here that we can't see. We can't see X-rays. We can't see gamma rays. We can't see ultraviolet rays. They're too small. We can't see ultraviolet, infrared rays, radar, FM, TV rays, shortwave, AM. They are too large waves. It's just amazing what all the different rays and waves that we just cannot see. Oddly enough, the difference in frequency is the difference in color. We have if you see something blue right here, I have a red arrow in top of blue. The waves are coming at you faster with the red arrow from what you see than what you see from the blue down here. It's just kind of even hard to imagine. Now, we have a formula for wave speed. The formula for wave speed is velocity equals frequency times the wavelength. So if we have a question down here that says a tuning fork has a frequency of 310 hertz, that would get that. The wavelength of the sound produced by the tuning fork is 1.32 meters. So that would be that. So it would just be a matter of multiplying out 310 hertz times 1.32 meters, which would probably be around the ballpark of 500, and velocity is meters per second. 500 meters per second would be the velocity of that wave. Now here you have what's the velocity of a wave with a frequency of 760 hertz. That's something you just put in on the frequency. Remember, frequency is hertz, and wavelength in this case is pretty small, 0.45 meters. So the wave speed would be just simply plug in 760 times 0.45 meters, which is somewhere around the 300 something range. As far as 300 meters per second is what that would end up being. Let's talk about one other slide here. The speed of a wave often depends upon the medium. You know, mediums that the waves have to go through. Sound is even faster, for example, in rock or in metal, And when you have two different mediums, like if this person's hammering on the wall here, if you're on the other side of the wall, you might hear it come through the wall, and then you might hear the sound go through the airwaves if you have like a door there. So you literally could hear boom, 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 two different sounds. So here's kind of the rule. Waves travel faster in solids, a little bit slower in liquids, and slowest in gases. So solids, liquids, gases are the order in which the speed is of the way sound travels. Now I just say sound because light is different. Light and the other electromagnetic waves, they're just different. They have a finite speed. It's not going to change. The speed of light is a constant. It does not need a medium. In fact, it'll even slow down a little bit when it does get to some of these others. It's not going to speed up because it is a constant. Final things we need to talk about are pitch and the Doppler effect. Pitch, you know, pitch is if you have a really high sound, you have a high pitch. If you have a really low sound, you have a low pitch. The higher the frequency, the higher the pitch. So if your sine chart has lots of up and downs, you will have a high frequency, a high amount of wavelengths per second. If you have a slow looking sine curve, then you have not as many wavelengths per second. So this would be the higher pitched voice, and this would be the lower pitched voice. I just had to do that, didn't I? Now, many sounds have a higher frequency the closer you are to it. Kind of like a train. If you're standing at the tracks and looking down the tracks and you hear a train coming, ding, 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 you hear the train coming. The pitch is going to fade as it goes past you and down the track. So if you step off the tracks and watch the train, you can still hear the ding dings, but it will sound differently to you. It will go ding, 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 like that, and you know it sounds differently. So that is called the Doppler effect. And you can see what's happening as you're walking here. The sound waves are coming to you, but as you are on the other side, the apparatus that's making the sound is going away, and therefore you don't have waves coming at you at the same frequency. Kind of like a fire truck here. It is going in this direction. So if you happen to be standing on the back side, the waves are not going to come at you as fast because of the movement here. And that is indeed called the Doppler effect. Hey, I hope you have learned a little bit about wave characteristics.